In the natural world today, the moon plays many important roles. It regulates the activities between nocturnal and diurnal animals. Many prey species reduce their activities on nights of a full moon, for fear that nocturnal predators can spot them, and various plant and animal species activities, from feeding to migrating to breeding, are affected, even regulated by the cycles of the moon. And of course, the moon, along with the sun, regulates Earth's tides. And the tides work to mix the substances of Earth, land, and sea, so that the materials required for life are always available, cycling through the ecosystem. But new evidence has come to light indicating the moon may have played a much greater role than simply regulating modern cycles of biological activity. Indeed, without our moon, Earth might not even have an atmosphere. According to leading theories, some 4.5 billion years ago, when Earth was barely 100 million years old, a Mars-sized object known as Theia slammed into the young Earth. The cataclysmic impact had first created a ring around the young Earth, which eventually coalesced into our moon. For hundreds of millions of years, the young Earth and the moon orbited very closely to one another and exerted powerful tidal effects on one another. Earth, considerably more massive than her small planet-sized moon, exerted a gravitational force that was so powerful that it acted like a subterranean tide, energizing and maintaining the moon's geodynamo, causing the moon to produce for a long time a magnetic field at least as strong as Earth's. The moon's magnetic field combined with Earth's magnetic field, forming a powerful force field which shielded our world from the sun. And this was very important because the early sun was far more chaotic and powerful than it is now, issuing as much as 100 times the solar winds and coronal mass ejections. Without the assistance of the moon's formerly powerful magnetic field, young Earth's new and forming atmosphere would long since have been stripped away. Much as we see the atmosphere of present-day Venus being stripped away by the solar wind, because Venus does not have a magnetic field. The fact that Venus has an atmosphere today at all is due, in part, to that the gases in the Venusian atmosphere are heavier than those of Earth's atmosphere, so some of them are harder for the solar wind to strip away, and due in part to Venus' occasional but massive volcanic activity, which replenishes the atmosphere from time to time. But after none too long, in the span of geological time, the moon's magnetic field died. But by the time it did, the sun was calmer. Nevertheless, the sun was well capable of emitting powerful solar wind, and to preserve our atmosphere, Earth needed a shield. Fortunately, Earth has its own powerful geodynamo. So long after the moon's magnetic field faded away, Earth maintained its own magnetic field, able to fend for itself. However, not independent of the influence of our moon. Indeed, recent findings indicate that without the moon, our own magnetic field would long since have died. What the magnetic field does is prevent charged particles from the solar wind from stripping away the lighter gases of our atmosphere. Gases like hydrogen and oxygen, which are necessary to make water and for the metabolic processes of life as we know it. Our twin world Venus has no magnetic field and long since lost nearly all of its hydrogen and oxygen. And neither Venus nor any of the other terrestrial planets have a significant magnetic field to speak of. Earth is unique in that it has a planet-sized moon, and that moon makes all the difference. The engine which keeps a magnetic field around our world is the Earth's geodynamo, a core of liquid iron alloy almost 3,000 kilometers beneath the Earth's surface. Scientists believe that near the time of the formation of the Earth, the core was about 6,800 degrees Celsius, and classical models indicate that its temperature should have cooled by about 3,000 degrees Celsius by this point. Yet data indicate that the core is only cooled by perhaps 300 degrees Celsius. It remains highly energetic and capable of producing a powerful magnetic field that surrounds our entire planet and extends deep into space. Clearly, the classical model of how Earth's core operates is in error. There is some unaccounted for source of energy that keeps the magnetic core active. This energy, it has been realized, most likely derives from the moon. Our moon is very large, and it is only 384,000 kilometers from Earth, close enough to exert a powerful gravitational or tidal force upon our entire planet. As mentioned earlier, this gravitational force creates the tides that we experience in the oceans. Tidal forces also deform the entire planet, except that Earth's solid portions, the continents and the surface beneath the sea, are much more rigid and deform only by millimeters under the tension of tidal forces. However, the iron alloy core of Earth is molten. It is liquid, and the tidal forces of the moon can affect it much more readily than the solid regions of Earth. The moon's tidal forces perturb the core enough to keep it in motion, enabling it to generate a powerful magnetic field over 4 billion years after it came into being. It is estimated that the gravitational/tidal power of the Earth-Moon relationship provides 3.7 terawatts of energy to Earth's core, more than enough to keep it highly energized across so long a time. Thus it is that the orbit of the Moon and its interaction with Earth through gravity keep our world shielded from solar radiation, and that allows us to maintain our atmosphere. But even with all that recognized, the Moon does yet more to keep our world fit for the maintenance of complex and intelligent life. Our world has a wobble. Its axis tilts between 22 and 24 degrees. That 2-degree difference might not seem like much, but it can have a very significant impact on the weather, especially the weather of the seasons, contributing greatly to when the weather is warm, leading to warm ages, and when the weather is cold, leading to ice ages. Presently, Earth's tilt is around 23.5 degrees, making for a colder period in our world's history, or at least what should be a colder period. Other factors, namely we humans, introducing carbon and other greenhouse gases into the atmosphere, are artificially warming the planet. But for our purposes here, what is relevant is that an axis tilt of a mere 2 degrees can steer the world from a tropical age to an ice age. But the proto-world, Theia, was a big planet. It hit our world with tremendous energy, enough energy to launch enough mass from our world to form the Moon and spin it off into orbit. And that energy was enough to set a wobble into our planet, much greater than the 22 to 24 degrees we presently experience. And there are other forces that lead to this wobble. Tidal forces from the Sun contribute, and changes in the distribution of Earth's mass also play a significant role in affecting the Earth's wobble. For example, when ice builds up on a continent or melts away, that adds a significant amount of mass in one area, and over time it can play strong effects in shaping how the world spins. Our Moon plays a tremendous role, however, in stabilizing that wobble. Astronomers estimate that without the Moon, Earth's wobble could vary by as much as 85 degrees, meaning sometimes the planet would lie practically on its side. So how does the Moon stabilize the wobble? Well, as Earth spins, centrifugal force causes it to be slightly wider at its equator. It's not really noticeable to the naked eye. But Earth is hardly a perfect sphere. The Moon's gravity holds Earth, exerting a bit more tug on its wider equator, allowing what we might think of as a place where gravity grips the planet, and thus the Moon's orbit is able to hang on to and stabilize the world. And it's a good thing for us too. If Earth were to lie nearly on its side, for many months out of the year, the side facing the Sun would be superheated and uninhabitable. And the side facing away from the Sun would likewise be super cold and uninhabitable. And during those periods when there was virtually no tilt at all in Earth's rotation, there would be no seasons. And seasons are essential for causing differential heating in Earth's gases and liquids, our atmosphere and seas. And this differential heating is imperative to mixing the substances necessary for life. The churning currents of air and sea carry carbon, nitrogen, phosphorus, and countless other materials around the planet. And without this movement of materials, life on Earth would be much more difficult. Fortunately for us, our Moon grabs our planet and stabilizes its spin, holding it between 22 and 24 degrees, just enough axial tilt to cause seasons, without going into the extremes that would make life almost impossible on our planet. At most any given time, a volcano is erupting around the world, but there are periods when volcanism greatly increases. And these periods are very likely attributable to the pull of the Moon's gravity interacting with the wobbling of Earth's rotation. When they coincide, their energy is amplified, and the world can undergo massive and global volcanic events. And these events have led to planet-wide extinctions, but they also bring the elements necessary for life from deep underground to the surface. We can see that the presence of our unusually large, small planet of a moon provides many benefits to our planet, stirring up our world's currents to mix the substances of life, providing guiding regulation to the biological activities of many species, energizing our planet's geodynamo, which enables our planet to have a strong magnetosphere that can protect us from our star's solar wind, and preserve our atmosphere, and stabilizing our planet's rotation against eccentricities developing in its wobble, that all by themselves could make life impossible on this planet if they were too large. Many scientists now believe that it takes more than planets in a Goldilocks zone in order to enable life. For that life to become complex and multicellular, a complex series of accidents must come together perfectly, aligning in such a way as to make a world ideal. The world must have the right chemical composition, the right balance between land and sea. Its orbit must be at the correct place from its star, The world needs to have a single star that is not overly active, and it needs to be a smaller star in order that the star might last long enough to give life, in particular complex life, a chance to evolve. And it may just be that for a planet to really have a good chance of harboring complex life, at some point in its past, a small planet must collide with it, in a way that is just right. A perfect collision that creates a moon that is massive enough to have a stabilizing effect on that planet, enough to stabilize its rotation and maintain a geodynamo across billions of years. And while, from what we now know, finding planets in the habitable zone of a star is not so unusual, finding a planet where random chance has managed to make all of these other influences come together in a way that is just right might be so rare that there is only one Earth in the entire universe. And thus, beyond Earth, the great silence, countless trillions of worlds beyond our star system and beyond our galaxy, but one so ideal as Earth, so rare as to make it the most precious thing in the universe. Thank you for venturing into the cosmos with me in this episode of Sky Story. Sky Story is part of the UNDERSTORY network, a collection of programs devoted to the study of the natural world. In Microstory, we study the invisible world of the very small. In UNDERSTORY, we examine natural history and issues of conservation. And in Sky Story, we look beyond Earth and explore the cosmos. There will be many more episodes, so to keep abreast, please take a moment to subscribe, and don't forget to hit that like button.